Allora, registrazione avviata, sì?
Sì.
E dove si può vedere? Ah, perfetto, questa. Cominciamo. So we continue. Grazie mille. So we continue to consider the deep learning problem for neural nets. The important thing is that this science is different from the theoretical mathematics in the sense that we have found some mathematical formalism. We have developed a series of algorithms, and then we can use these algorithms, and usually in mathematical sciences, one thing to finish his job. In mathematical engineering is not so. When in mathematical engineering one finds some algorithm, one finds some mathematical formalism and develops some algorithm to resolve the problem. Really, in reality, such algorithm should be studied and should be supplementary studied and analyzed in the sense that if we have some recursive procedures, is their procedures converge? Are they converge to the result which we need, or it converges to absolutely other result, and so on? There are a lot of problematics appear which need a thorough analysis. So first of all, we have considered the last lecture is that there is problem of there is a problem to learn this algorithm and to learn the neural net, and there is some slowing of our learning process. So in order to avoid the slowly learning procedure, one can consider the post function or activizing function different from the canonical function, like the quadratic cost function and like the sigmoidal, yes, logistic function, sigmoidal activation function. Why? We have considered some very simple example of one neuron, yes, and we take some task, yes, to find out the parameter of this elementary, yes, toy neural net, in the sense that it have a response for input 1, the response is 0. Which coefficients W, yes, weight, and bias B should be in the sense that it behave in this manner, yes. For input 1, it returns the output 0. So it can guess how to do. So to take casually some numbers and to combine and to calculate, but it is not a good way. We are interested to make some regular procedure, procedure which learn this elementary neural net. So learning this neural net, we can see that up to 300 epochs, yes, stages of learning, yes, 300 epochs or stage of learning. We have very good decade, yes, decade to zero, the cost function. So very good convergence of our criterion of our learning. And we also have very good conversion of weight coefficient and bias coefficient. Then we can choose initial value of the parameters different and very big, far from the real parameters which we need. And we begin to see that the neural net having big mistake initially begin to learn very slowly. In fact, first 150 epochs, yes, stages, it does not learn. So the coefficients values together with the cost function have no essentially changes. And then after 150 epochs of learning, it begin to learn and to learn successfully and really fast. Why we have such problem? We told the past session that because our activation function sigmoidal have it has some growth, and when the argument is enough big, yes, its gradient become very low because it has asymptotic horizontal line equal to 1. So the problem is in that the gradient of cost function by weight parameter and the differential gradient of cost function by bias parameter give us multiplier sigma prime of z. Yes, it is derivate, and when the z is rather big, then sigma prime of z is near to 0. Yes, near to 0 here. Doesn't grow more. So this is why we have very slow learning, and we need to avoid this situation. How we avoid this situation? By introducing a new cost function, so-called cross entropy cost function, which is, you see, minus 1 by divided by n, the summation over all learning samples. Yes, x it is any learning sample. Y logarithm natural a plus 1 minus y logarithm natural 1 minus a. So Y is the desired output, A is our activation function in the neuron. Yes, so response of our neural net. And we can assert that such a function has the typical behavior of the cost function, in the sense that it is not negative, it is positive. And if the neuron's actual output is close to desired output, then the cross entropy will be close to zero. So typical necessary conditions which satisfy the classical cost function, something like quadratic cost function. But the very pleasant property is that if we calculate the gradient of new cost function, yes, our cross entropy cost function, we can obtain that by these properties, the property of the activation function, logistic activation function, we have that this gradient doesn't depend on the derivative of sigma and depend only by the difference of the response of the network minus the desired result. It's very good. So bigger this distance, yes, this difference, bigger the values of this term. So more contribution of difference, learning difference, it can bring. So our neural net begin to learn faster. It's very pleasant thing, yes. And in the similar way, also the gradient of cost function, respectively of the bias parameter, also doesn't depend on the derivative of the function sigma. So it was the brief repeating of the past lecture. Now we continue to discuss some very subtle circumstances connected with the learning process. So first of all, we told that there is some speed down of learning, yes, of learning procedure. So we can have very slow, yes, slow, become slow our learning procedure. And the second thing, can be that we can begin to learn, our neural net. And what happened? We can see that the several stages of learning, yes, several epochs. We have the progress of improving the cost function, and then we find out that the learning not more move to the desired result, but begin to oscillate or to go to some wrong values which correspond to absolutely other statement of problem. And we will discuss why it can succeed and how to avoid this problem. So that is why the general title of this lecture is Improving the Neural Net network learning. And first of all, latest define the cross entropy function in general case. Before we have considered very elementary neural net, which consist of only one perceptron and several input signals and one output. Now we want to generalize the cross entropy cost function for arbitrary many neural multi-layer network. So let us consider the parameter of such neural net as y is y1, y2, and so on are desired values of the output neurons, yes? And A1, L, A2, L, and so on, the actual output values, yes, of the output layer L capital. So we define the cross entropy to many neural multi-layer network as follows. C is the summation on X all training samples. Summation by J. J is the number of concrete neuron in the last year layer L. Yes. And we summation of yj logarithm natural logarithm a j l plus 1 minus yj logarithm natural logarithm 1 minus a j l. So some generalization of our cross entropy function for one. Now for any number of neurons and multi-layer. Now summing over the output neurons. Yes, so it is this now summing only over the output neurons. And we expect that such generalization avoids a learning slowdown in many neuron networks, and really it succeeds. Let us consider why and due to which processes. Returning to the quadratic cost function, yes, let's rewrite it. 1 by 2 and summation by x and j, yj minus ajl square. So what is it? It is Pythagore lengths of the vectors of deviations between the desired result and real result of output layer, yes, of our neural net, where again, what is output result? It is the weighted sum plus biases. We calculate this value at each node of our neural net. Yes, for example, in the layer output layer L capital, yes, ZL, and then we take the sigmoidal function of activation. Yes, this is the formula. This is it is form. It is easy to verify that for the quadratic cost, the partial derivative with respect to the weights in output layer L is can expressed as 1n akl minus 1, then the difference between ajl minus yj, so the linear error multiplied by derivate sigma prime of zeta JL. And this term, sigma prime, can break our velocity to learn our neural net. Therefore, the multiplier sigma prime causes learning to slow down when the neuron learns towards the wrong value. Yes. So more bigger difference of this big difference of the response reply of the result of our neural nets from the desired result. More slowly this neural net can learn. So we for the cross entropy cost, we can write down an output error for single training example X. Delta L, it is AL minus Y. And introducing the single training output error, we can use the fundamental equation BP4 for backpropagation, yes, and we can obtain from this error the gradient of cost function, respectively, of the weighting coefficient 5, 4, and the gradient of cost function, respectively, of on the bias coefficient BJL also. So we can see that this gradient doesn't contain the multiplier term sigma prime of something. So we have not here the slowdown of learning, which is our scope. Using now the cross entropy to recognize our handwritten digit, yes, collected by the Institute of Standard of United States. So the cross entropy will be used by learning by gradient descent and backpropagation, as usually. Firstly, in first lecture, we have constructed some neural net containing one hidden layer with 15 hidden neurons. Now we consider 30 hidden layers. The output layer, as usually, will contain 10 neurons, and input layer contain 784 neurons. Okay. So the result from running this neural net using the old quadratic cost function give us to learn a network with the result of 95.49% of accuracy. this is pretty close to the result we obtained in the first lecture using the quadratic cost. Let's look also to the case where we use not 30 hidden layers, but we have sophisticated our neural net to 100 hidden neurons. And using cross entropy, we keep the parameters, other parameters the same. For example, the speed of our speed eta, parameter eta, speed of our learning, and so on. In this case, we obtain the accuracy of 96.82%. It is very good and pleasant result to improve, essentially improve our recognition of handwritten digits, and the error has dropped, we can constatate, from 3.41% to 3.18%. Where does cross entropy come from? Why we firstly introduce the quadratic cost function, and it was very good function like criterion to learn our neural nets, and now we introduce the cross entropy, a new cost function. So consider now what one perceptron model, yes, weight W and bias B, only two parameters, with quadratic cost. And we have the following gradients. It is very simple to verify. Yes, A sigma prime of Z and A sigma prime of Z. And the term sigma prime of Z can cause the learning slowdown described earlier. In order to eliminate, how can we find out now the cross entropy function, the form of cross entropy function? In the following way, how can we arrive to this idea? So in order to eliminate the term sigma prime of Z, which causes learning shutdown, slow down, we shall look for a cost function, some cost function C, which depends, of course, of training sample X, which for a single training example or training sample would satisfy equations dc by dwj is xj a minus y, and dc by db a minus y. So it is what we need to obtain, we want to obtain, and we don't depend on sigma prime of z. Starting from this equation, let us show that it is possible to derive the form of the cross entropy simply by following our mathematical intuition. To see this, note that the chain rule, by the chain rule we have dc by db is dc by da activation function multiplied by activation function sigma prime of that. But for logistic function sigma prime of z, it is very known formula is sigma z multiplied by 1 minus sigma z. It is a 1 minus a. So in this situation, dc, so the first formula, dc by db is equal dc by da, and sigma prime we can substitute by this expression. So A dc by dA, A 1 minus A. Taking into account the relation dc by dB A minus y, yes, we can substitute it. So we have dc by dA is equal A minus y, A 1 minus A. Integrating the last relation by parameter A, we obtain the solution of this equation. C is equal explicit expression for the cross entropy and some constant. And then we should average but all the constant. So intuitively we have obtained the expression for the cross entropy by starting by the presuppositions that we should eliminate this term multiplier sigma prime of z. Okay, what about the intuitive meaning of the cross entropy? What is it? What is this function mean? Very, very strange thing. Roughly speaking, the idea is that the cross entropy is a measure of surprise. We expect some result and we don't expect some result. So the cross entropy increase when we don't expect some results, and more surprise of our result calculation result, more big the bigger the value of our cross entropy value of cross entropy function value. Okay, suppose we think of RA as our neurons estimated probably that y is 1. For example, we recognize some digit, yes, y is 1. And 1 minus a is estimated probably that the right value for y is 0. Then the cross entropy measure how surprised we are. So how we expected such value or less. We get low surprise if the output is what we expect, and we high surprise if the output is unexpected. Some plausible hint can be done by craft inequality in information theory, and perhaps in some lectures we can look at this argument. Now, the other very important improving procedure is the introduction of softmax activation activization function or activation function or activization function. So firstly, we dealt with the function sigma of the z, yes, and this activation function, we know very well what is it. It is the logistic function. And it is a very good function. Why it is very good? It is smooth, and it constrain the small increment of argument, have small increment of the function value. Yes, so we have not big surprises using this function, so we can smooth our learning procedure, and it is very important. So softmax. And softmax activation function is the alternative other approach to the problem of learning slowdown. Softmax is worth understanding in part because it is intrinsically interesting, but in part because it effectively works in learning of deep neural networks. And very important that softmax activation in some layers is very good idea to adjust and to optimize the procedure of deep learning in some complex deep neural networks with big number of intermediate layers, of hidden net layers. The idea of softmax is to define a new type of output layer. We tell only about the output layer for our neural network. It begins in the same way with a sigmoid as with a sigmoid layer, by forming the weighted input as usually, the argument of our activation function in the neuron number J in the layer L, in the output layer A, from the case neuron of the previous case layer of the previous layer. The neuron number A of the previous layer plus bj, so it is biasing of neuron J. So we construct this weighting sample plus bias, plus our shift, and to this argument, however, we don't apply the sigmoidal function to get the output. Instead, as in a softmax layer, we applied the so-called softmax function to our argument zeta jl, and so we applied the exponential functions, this exponential in the power zeta jl divided by summation of these exponents in all nodes of the output layer L capital, where is in the denominator we sum over all the output neurons, K. Comprehending also the J's neuron. It's certainly not obvious why we want to use this function and how it can help to avoid the learning slowdown problem. But it not only to help to avoid the slowdown problem, but it also renormalize our output values. In which sense we shall tell some later. It is certainly not so. To better understand the softmax function, suppose that we have a network with 4 output neurons, and 4 corresponding weighted inputs, which will denote zeta 1, zeta 2, L, zeta 3, and zeta 4. So for the output layer L big, we have four parameters, okay? waiting input. And then we can construct the softmax function 5.8 for A1, A2, A3, and A4. For zeta1 equal to -1, zeta2 equal to 0, zeta3 equal to 1. So we have the graph of softmax function 5.8 for different fixed values in this case -1, 0, and 1, and variable zeta4, it is red. With increasing zeta4, you will see and increase the corresponding output activation zeta A4, excuse me, it is A4, L, and decrease all other, and decrease all other activation. It is very good, you see, because when, for example, we train, for example, our network for recognize of handwritten digits, yes, what we need that by our training, one of these neuron tend to take a value near 1, and other to take values near 0. And if, for example, will be 0, 0, 0, here 1, then 0, 0, 0 means that the neural net recognizes 3. You see? So it is very, very useful function from this. So we don't have to make some comparing of the values of our activation function of output perceptrons, but we see the probability to find, for example, 3 like our input x equal to 3, and so on. So we can evaluate easily and in very clear mode the response of our neural net as recognition of handwritten digits. So figure 5.1 shows a graph of the corresponding output activation for different inputs. And with increasing zeta 4 and zeta Z4 L should increase if we confirm that it is this recognized digit, and see an increase in the corresponding output activation A and decrease in other output activation. Similarly, if you decrease zeta for L, then A for L will decrease and the other output activation will increase. In fact, so we by such procedure of learning, we have very clear indication about the result of recognition. Okay, the reason is that output activation are guaranteed to have a sum 1. So this summation of AJ is equal to 1. Notice also the all output activation are all positive since the exponential function is positive. Yes, yes. So it is positive, and since it is the summation by I by all nodes in the output layer is equal to 1, so it is a discrete probabilistic distribution, which is not true for example, for cross what is softmax and the other cross entropy. For cross entropy, it is not so. So the entropy function also is introduced for entropy of probability, yes, and for entropy of information flow, and it deal with it is P and Q, and it, for example, P logarithm P minus 1 minus P Q logarithm by Q. You see? So the fact of the soft max layer outputs a probability distribution. Again, the soft max procedure deal only two layers, the last and pre-last layers, L big and L big minus 1. In many problems, convenient to be able to interpret the output activation, estimate of the probability and the correct output is J. Okay? So, for instance, for classification of our first problem to recognize handwritten digits, we can interpret AJ as estimated probably for corrected digit classification is J. By contrast, for if the output layer was a sigmoid layer, then we certainly could not assume that the activation formed a probability distribution. So it is also the cross entropy function is some generalization of entropy in the sense that it not deal with probabilistic distribution. And hence, with a sigmoid output layer, we don't have such a simple interpretation in the output activation. Then very interesting things, very interesting properties are monotonicity of softmax. What is the monotonicity of softmax? You see, so the gradient of our activation function AJL by by weighting coefficients is positive if J equal to K and negative if J not equal to K. As a consequence, increasing that KL is guaranteed to increase the corresponding output activation AJL and will decrease all the other output activation. It is monotonicity of softmax algorithm, not non-locality of softmax. Nice thing about sigmoid layers is that the output AGL is a function of the corresponding weighted input. For example, AJ is the sigmoidal function sigma of zeta JL. It explains why this is not the case for a softmax layer. Any particular output activation depends on all the weighted inputs. Then also, why is softmax? Because of the probabilistic distribution, like the last output layer, yes, soft in the sense that the summation is equal to 1 and any of every of the activation values, yes, they softly move by the procedure of learning. It is soft. The learning slowdown problem. Why now it resolve? It prevent slowdown problem. We have discussed the softmax layers of neurons. So softmax is the procedure with the last layer, output layer of neural net. But we have not yet seen how a softmax layer can avoid the learning slowdown problem. To understand, let's define the log likelihood cost function, logarithmic likelihood cost function. Likelihood is a typical expression in probability theory and mathematical statistics. So for any x, training input to the yes, training our sample, yes, which is especially prepared to learn our neural network, and y is the corresponding desired output, we introduce log likelihood cost. You see, logarithmic likelihood cost as follows. C is minus logarithm AJL. So for example, if we are training with the training set of American Standard Institute, yes, MNE East, Standard American Institute for Images of handwritten digits and input and image of a set 7, then the log likelihood cost is minus logarithm natural A7L. If the neural network fits good, it should return the value A7L near to 1. Hence, minus logarithm A7L is near 0, which is the property of cost function. So the log likelihood cost 5,9 behaves as we'd expect a cost function to behave. What about the learning slowdown problem? To analyze that, recall that the key to the learning shutdown in the behavior are the gradients dc by the wj. So gradient of cost function by weighting coefficient and gradient of cost function by bias parameters. Using definition of log likelihood cost function, yes, one can calculate the partial derivatives. Yes, it is very, so we can calculate from here partial derivative, and dc by dbjl is ajl minus yj. and dc by the parameter of weighting parameter is akl minus 1 ajl minus, so again the error of first grade, between the result and the desired value. So we have not dependence on the derivative of activation function here and here, but only on the difference between the value on the output neurons and the desired responses of the work, properly like the cross entropy cost function. So the cross entropy cost function is very good cost function. It avoid learning slowdown, but the output AJ are not probabilistic. There is some not dependence on the what is this comments means? Can you discuss with me? Do you have some questions? Please. You have close your microphone. So you should activate your microphone. Okay. Let's continue. Let's continue. And the soft mass plus log likelihood cost is also very good cost function, which also avoid learning slowdown, but arrange the output layer in the sense that its values present probabilistic distribution. It's very pleasant. Overfitting and regularization, as you told you at the initial, we have some problem of improvement or worse doing the procedure of deep learning of our neural nets. So now let us tell about other dangers, not only slow down of learning procedure, but also overfitting and the procedure of regularization to avoid overfitting. Overfitting, it is first we have improvement in the training procedure, but beginning from some moment we begin to get worse results, and we should stop these training procedures. Otherwise we can break our procedure and to come to absolutely other results other that we try to obtain. The Nobel Prize winning physicist Enrico Fermi was once asked his opinion about the mathematical model of an important unresolved problem in physics. And he asked, how many free parameters could be set in the model? And the answer was 4 parameters. And Fermi replied, he was very skepticism had about this problem. Fermi replied, I remember my friend Johnny von Neumann used to say, with 4 parameters, I can fit an elephant in the system. I can fit elephant in the system. And with 5, not with 4, with 5 parameters, I can make him wiggle his trunk. So wiggle trunk in all the directions. Too much spaces for 5 parameters. Fermi and von Neumann were suspicious of models with 4 parameters. Our 30 hidden neuron network for classifying the handwritten digit dataset, okay, has nearly 24,000 parameters. That is a lot of parameters. And if we increase our hidden neurons in hidden layers up to 100 hidden neuron in hidden layer, so our network will have nearly 80,000 parameters. And state-of-the-art deep neural nets sometimes contain millions or even billions of parameters. Should we trust the results? Nothing to do, we should trust. Consider now only 30 hidden neuron network as we designed before, with its 23,860 parameters. But we won't train the network using all 50,000 dataset training images as American Institute give free access. Instead, let us use of these 50,000 samples for training, only 1,000 training images. So we'll train in a similar way to before, using the cross entropy cost function, so the best thing, with a learning rate of eta 0.5 in a mini batch size of 10, like, yes, so random sample choose in training dataset. Okay. However, we will train for 400 epochs, not 300, 400 epochs, somewhat larger number than before, because we are not using as many training examples, so not 50,000, but 1,000. So let us look now the way the cost function change and go to this procedure. There are some standard procedures in Python packages about artificial intelligence. So it is very standard procedure. And the cost on training data, we omitted first 200 epochs, and we begin to consider from 200 up to 400. Okay, so we have enough good decade, yes, decrease of the cost function. Now let's we look at how the classification accuracy on the test data changes over time. And here we have some problem. In the first 200 epochs not shown, the accurate accuracy rises to just under 82%. Yes, something like 82%. The learning then gradually slows down. Finally, at around epoch 280, you see, the accuracy pretty much stops improving. Accuracy. So we have some natural stop of the learning process. So we should verify such events, and we should register such events. Just like the model that Fermi disliked, what our network learns after epoch 280, no longer generalizes to the test area, and so it's not useful learning. We say the network is overfitting and or overtraining, so overfitting or overtraining beyond epoch 280. So why we have trunced the number of training samples. Yes, we have taken only 1,000 when we have at least 50,000, because we have 50 plus 10,000 for verification. Okay, so in this situation, the obvious way to detect overfitting, you see, there is slow, yes, there is the procedure of slow of our learning, and there is the procedure of overfitting also. Okay, so we need to keep track of accuracy on the test data as our network trains, and we should stop at the moment when our accuracy is not more improved. Okay, we have been looking for so far an overfitting when we are just using only 1,000 training image. It is not very good number if we frankly tell. What happens when we use the full training set of 50,000 images? Of course, the situation should improve. We'll keep all the other parameters the same, 30 hidden neurons, learning rate always 0.5, mini batch size of 10, but train using 50,000 images for 30 epochs, only 30 epochs. So we have red, it is accuracy on the training data, and blue, accuracy on the test data. Test data is our testing set, and red is training set. And we remember that the training set in our situation is 1,000 training image. Overfitting is still going on, but it's been greatly reduced. Our network is generalizing much better from the training data to the test data. So if we use for training some restricted number of images, so the neural net adapts to this training image and begin to recognize they are very good. But a very big set of data, training data, but used for verification, it not recognize very good. Unfortunately, training data can be expensive. So, in general, one of the best way of reducing overfitting is to increase the size of the training data. But the training data can be expensive or difficult to acquire, and it is very often. So it is not always a practical option. So now, how to batch this factor? It is so-called procedure of regularization. So regularization is a way of reducing overfitting, and mathematically it is introduced of some in the cost function of some additional term. So correcting additional term, but in the terms of the neural nets topology, it is the temporary exclusion of some pathways and some neurons, intermediate neurons. It's very interesting procedure. So we see that in the weight decay or L2 regularization, weight decay or L2 regularization, we introduce some new cost function which consist the usual part. The first is the usual expression for cross entropy as before, but we then to add some second term, yes, lambda divided by 2n, the summation of all weight values, or square weights, okay? And n is the number of training samples. So this term is scaled by a factor lambda divided by 2n, where lambda is known as a regularization parameter. So lambda is special parameter, so-called regularization parameter. How to choose this parameter? It is a very interesting question, and I try to explain it later. So, and n is as usual the size of our training set. Of course, it is possible to regularize other cost functions such as the quadratic cost, which have the same problem of overtraining. So in this situation, we take our quadratic norm, yes, but Pythagorean norm, and also we adjoined the term of square weight. So means square weights. In both cases, we can write the regularized cost function as new cost function is the traditional cost function plus the mean square weighted function, where seed 0 where the C0 is the original unregularized cost function, yes, or quadratic cost function, or our cross entropy function, cost function. Why such corrections should help reduce overfitting? Let us apply our stochastic gradient descent learning algorithm in a regularized neural network. So we can write down dc by weighting coefficient is equal to dc0 by dw plus lambda by nw. And what is about dB? It is nothing change, only by weighting change the expression of the gradient. The gradient by weight and the gradient zero by bias terms can be computed using back propagation as described before. So we can rewrite the iteration of training by back propagation. The partial derivatives with respect to biases are unchanged, and so the gradient descent learning rule for the biases doesn't change from the usual rule. So B will be iterate by substitute B minus eta. Yes, the velocity of training dc0 by dB. And the learning rule for weights become with some supplementary fact with some supplementary term w substitute by w minus eta dc0 by dw minus eta lambda by nw. So we can present in our equivalent form. This is exactly the same as usual gradient descent learning rule, except we first rescale the weight w by a factor 1 minus eta lambda by n. This rescaling is sometimes referred to as weight decay, since it makes the weights smaller. In this case, the cost on the training data decreases over the whole time, much as it did in the earlier unregularized case. And the descent of the cost on training data now is from the epoch 200 to epoch 400. First 200 epoch are omitted. Okay, so we have the decreasing of the cost function as in normal good learning procedure. But the accuracy on the test data now increasing linearly by superposing some random noise. So it is the numerical verification of improving our correction of the cost function in order to prevent the overtrain. Okay. So let us now finish, because the next time I will explain mathematically, not only numerically, why the accuracy now continuing improve, and we have no overtraining more. Okay, so do you have some questions?
No, I don't have questions. Thank you.
Oh, so the main task of my lecture was, you see, after our consideration of the construction of neural nets, after our introducing of all the mathematical apparatus, after the complete algorithmic construction, seems to be we have finished our task, but it's not so. In engineering mathematical problem, the problem only begin, and there are a lot of examples when, for example, we have some numerical analysis which ask a lot of forces to correct some mathematical formalism in order to do it very useful and very effective. Because you see, we have some iterating procedures should converge to our desired results, but it is not always such. So we should make some flex, some criteriums of the good convergence of our procedures to the desired results, and to have some new corrected instruments which prevent some problems in order to get some results. Okay, so thank you for your attention. Other question? No. Okay, so I finish my registration and see you the next Wednesday. Next Wednesday. So today, unfortunately, not Thursday, but Wednesday. I don't know if the students, doctorants knew this fact, and the next lecture will be also the next Wednesday. So bye-bye and have a nice day.
Goodbye.
Bye.